Hello, I'm back again with another branch of physics known as optics. This branch of physics is about light. Light, in other words, we call it optics, and it's one branch of physics. Let's think about the world without light. What do you think if there is no light, and what happens to this world? Is it possible for human being to live? Is it possible for plants to live? Is it possible for this world to exist without light? Is a question. So think about it. If there is no light, green plants cannot prepare food. If green plants cannot prepare food, what do we eat? Think about it. So you can imagine that without light in our house, what is going to happen? Without light in our environment, what is going to happen if there is no light completely for one day in the whole universe or in one city? What will happen? Think about it. So a branch of physics that studies about optics and optical devices is known as about light and optical devices known as optics. So that is why we need to study the properties of light. This chapter has three sections. The first one is the nature of light, and the second one is the color and electromagnetic spectrum, and the third one is polarization and scattering of light. So let's start with the first section, the nature of light. Light is a small but important part of electromagnetic spectrum. Everything you see either emits light or reflects light. The sun emits light. The light bulb emits light. The moon reflects light. Mirror reflects light. All other objects around you that you see but not the sources of light, they are all light reflectors. The waves that make up light can travel through a vacuum, which is empty space, unlike mechanical waves like sound wave. Sound wave cannot travel through empty space or vacuum. It only travels in a medium, which could be either gas, solid, or liquid, but light can travel in a vacuum where there is nothing. Nothing can travel faster than light in a vacuum. We use the symbol C, which comes from the word celerity, meaning that the speed or the swiftness of movement, to represent the speed of light. Approximately, the speed of light in a vacuum is about 300 million meters per second. Because the speed of light is so large, its value is difficult to determine. The following are some of the important milestones on the road determining the speed of sound. Galileo he did an experiment in the first attempt to measure the speed of light, and his assistant used two lanterns or two lamps, and they opened the shutter of the lantern, and the assistant, who was positioned at a large distance away, was instructed to open the shutter of the second lantern. As soon as he saw the light of the other lantern, which is opened by Galileo, and then he attempted to measure the time that elapsed before he saw and the returning light from his assistant's lantern. Seeing no delay, he concluded that the speed of light must be very large, too large to measure with such an experiment. So he tried to measure the speed of light. What does it mean in other words? What it means is, let's say you have a mirror at one end and you shine the light from one source, and right away the light hits the mirror and reflects back, and there is no measurable time in between that. And another observation is a Romer's observation. The first to give a numerical value to the speed of light was a Danish astronomer whose name is known as Ole Romer. While using ellipses of the moon of Jupiter to solve the problem of determining longitude, Romer found that the time of these ellipses varies during the courses of the year. So let me rephrase this statement. Romer's observation, he is the first to give a numerical value to the speed of light while using ellipses of the moon of Jupiter to solve the problems of determining the longitude. Romer found that the time of these ellipses varies. Romer observed that light requires about 16 minutes to travel from one side of the Earth's orbit to the other side. Using this value, he calculated the speed of light to be 200 million meters per second, while the modern value is 300 million meters per second, which is very close. Experiments. The first laboratory measurement of the speed of light was performed by the French scientist Armand Fiajo. The basic elements of his experiment are shown in this figure. The source of light, a transparent mirror, and the notched wheel and the mirror. So he, as you see, the light traveled from here and passing through a transparent mirror, and again passing through one of the notch in which, the notch that is rotating, the wheel that is rotating, it passes through the notch and then it hits the mirror and reflects back while it is rotating. And then when it comes back and hits again, there is observer right there. So what you have to do is you measure the distance from here to here, and again you measure how far it rotates. From the rotation of the wheel and the time it took to go back and forth, and the speed of light is measured for the first time. Fiajo's experiments, this is the first experiment or the first laboratory measurements of the speed of light, which was performed by a French scientist named Armand Fiajo. The basic elements of his experiments are given in the figure, which is there is a source of light, a transparent mirror, and notched wheel and mirror. And you observe, of course, as a human being, you have to be there to measure this. So in this apparatus, light passes through one notch in a rotating wheel, which is this one. It passes through one notch, which is, and then this is a rotating, and travels to a mirror, which is far away from this point, that is at a considerable distance away. If the time required for the light to travel to the far mirror and back is equal to the time it takes for the wheel to rotate from one notch to the next notch, light will pass through the wheel and on the observer. So by measuring the rotational speed of the wheel and the distance from the wheel to the mirror, Fiajo was able to make an accurate measurement of the speed of light, and his value was about 3.13 times 10 to the power of 8 meters per second. So this 3.13 times 10 to the power of 8 meters per second is almost equal to the value that we know today, which is 2.99998 times 10 to the power of 8 meters per second. And the other nature of light is the Doppler effect. If you guys remember, we have seen how sound has, or a wave has a Doppler effect. And again, light is a wave, and therefore it has a Doppler effect. The Doppler effect applies to light as well as sound. It changes the frequency of light waves just as it does for sound wave. For the source of light, with the frequency f of the source and the speed of the source, which is v of the source, relative to an observer, the observed frequency f observed is calculated by the frequency of the source times 1 plus or minus v of the source divided by the speed of light. The plus sign is used when the source is approaching the observer, and the minus sign is used when the source is moving away from the observer. The Doppler effect applies not only to light and sound, but it also applies to all types of electromagnetic waves, including light waves, radio wave, microwave, and so on. Example: how the Doppler equation can be used to determine the change in frequency of radio waves. So the question is, what is the frequency? An FM radio station broadcasts at a frequency of 88.5 megahertz, M capital. If you drive your car toward the station at 32.0 meters per second, what change in frequency do you observe? So we can find the solution in a frequency f observed minus f of the source by rearranging the Doppler equation f observed, which is equal to f of the source, into 1 plus v of the source divided by c, and this gives you f observed minus f of the source is equals to f of the source times v of the source divided by c. So we know that the frequency of the source is 88.5 megahertz, which means a million hertz, then times v of the source, which is 32 meters per second, divided by the speed of light, 3.00 times 10 to the power of 8. When you do this calculation, there will be 9.44 hertz. Thus, the frequency change by 9.44 hertz, which is only 0.0000944 megahertz. No need to retune your radio, your car's radio as a receiver, because the change is very, very small, so that you can just tune your radio once and then you can listen to the radio. And another thing that we need to know is, we know that in physics or in science, we always hear that the statement that says the universe is expanding. American astronomer Edwin Hubble discovered that light from a distant galaxies is a Doppler shifted. In fact, he found that the greater the distance to a galaxy, the greater the Doppler shift. Furthermore, he found that most galaxies are moving away from us, that their speed is directly proportional to their distance. So when he says that most of the galaxies are moving away from us, which means the universe is expanding. So how does he know that? Hubble observed it. What he observed is the light that comes from these stars or these galaxies. So this idea is very clear that it is supporting Big Bang theory. According to this theory, the universe started in a hot, dense state and then expanded rapidly outwards. So how does he know whether the universe is expanding? How he knows is, let's say if you take a star or one star at one time and you measure the light that comes from that star, and then let's say it has a frequency of either a red light or a blue light or a green light, those 7 colors that we can see. So if the star is close to you, initially it has to show you a kind of blue light, which means closer, something with a higher frequency. But over the time, what is observed so far is every galaxies, every stars, their light is going from high frequency to low frequency, which is from blue to red. So what does that tell you? The universe is expanding and the stars are getting far away from us. Light is certainly a wave. Light displays all properties that define a wave, which could be amplitude, frequency, wavelength, and speed. Even though light also displays some properties that are associated with particles, which means light has a dual nature, a particle nature and a wave nature. As a wave, it has a speed, it has wavelengths, it has frequency and amplitude. As a particle, it might have a mass. To understand this behavior, you might say that light bottles. It is energy, rather than delivering from a tap. So let's look at these two figures, figure A and B. In figure A, it indicates that a wave with energy that can have any value is like a water coming from the tap, which can provide any amount. But in the case of the second, the bottled water, which is totally different, that water amount is limited. Bottled water comes in a discrete package, the individual bottles, and you can get 1 bottle, 2 bottles, 3 bottles, or more. This is like energy carried by a light wave. It doesn't come in any amount at all, but it only in bundles of energy in a fixed amount, just like bottled water, which we call them photons. The bottled up packets of energy in a beam of light is referred to as photons. You can think of photons as a particle of light that carries energy but has no mass. It carries energy but has no mass. Photons are what give a light its particle-like nature. One final mystery of light involves its speed, as measured by different observers. Albert Einstein made the following bold prediction in 1905. All observers measure the same speed of light regardless of their speed relative to one another. Whether you are traveling at a higher speed or at a lower speed, when you look at the speed of light, every observers measure the speed of light to be the same. So look at this picture to see how remarkable this prediction really is. Consider the following example. If you look at this example, suppose a friend zooms by you in her spaceship at 90% of the speed of light. After she goes by, you shine a beam of light in her direction, which is indicated right there. So this is your friend, which zooms by the speed of 90% of the speed of light. So even though the spaceship moves with the speed of 0.9 c, which means a 90% of the speed of light, your friend sees a beam of light going past her at 100% of the speed of light. Both you and your friend measure exactly the same speed of light beams, even though she is moving very fast relative to you. The fact that all observers measure the same speed of light leads to additional interesting consequences. Among these are the fact that clocks run slow at high speed and the metric stick shrinks in length. Let me say this statement again. Among these are the facts that are clocks run slow at high speed and metal sticks shrink in length. So that is all about section 15.1. It is simply introducing you to some general properties of light, and then I'll see you on the next section.